Welcome, ladies and gentlemen, to a presentation on quantum key distribution, presented by Devin Tamote, Sophia Gonzalez, Tejas Gopal, and Samin Chowdhury. This message is brought to you by Pepsi. Quantum key distribution in a nutshell is a secure communication method that uses quantum protocols and procedures. This is mainly used in cryptography to produce secure keys that can be used to encode and decode data. This, of course, utilizes the no-cloning theorem to ensure messages exchanged between users are not duplicated or intercepted. This methodology ensures messages between a sender and receiver were not intercepted by anyone else, which is a very important thing in today's modern world. The motivation behind this is to ensure that there is secure end-to-end encryption. Currently, information is being transferred over a line which is susceptible to hackers. By utilizing the no-cloning theorem, we can use photons as a mean of information transfer to prevent duplication of a message. Before we begin, we should take a second to review the no-cloning theorem. Cloning is technically not impossible when it comes to quantum computing. It just requires information that is impossible to know before making measurements. If a strict basis is to follow, cloning is achievable. However, cloning would only work for that given basis. To clone a state that belongs to any kind of base, this would be absolutely impossible to do without prior knowledge of the incoming state. So in summary, you can simply not clone qubits. Some prerequisite knowledge that would be useful to know before I go into this topic is the polarization of light. Light is polarized, and polarizers can filter out certain light waves. Since light is made up of photons, these polarizers can filter out which photons in a certain spin can get through or not. It is from these polarization orientations you can create new bases for measurements. As you can see here on the image on the right, the first polarizer is set in the vertical orientation. This means that the incident beam going through it will only have the vertical polarized light wave go through. As you can see, the second polarizer is set in the horizontal position, meaning that the vertical polarized light will not go through, since it is not horizontal. Some more things to know is that due to the quantum nature of light, if photons coming into polarizers that are oriented 45 degrees to the original basis, they will have about a 50% chance of going through. To relate these things to class, we can have the horizontal and vertical bases refer to the 0 and 1 bases, and the diagonal and antidiagonal bases refer to the plus and minus bases. As you can see depicted in the image on the right, we can see that the diagonal and antidiagonal bases can be written in form of the 0 and 1 bases from above. Using this information, we can infer that a photon in a 0 or 1 spin state would have a 50% chance of going through a polarizer in the plus or minus orientation, and vice versa. And now we begin the actual encryption itself. Let's handle the simple case between a sender and a receiver. Alice generates a string of bits and will send them using either the horizontal and vertical bases or the diagonal and antidiagonal bases to Bob. Bob will then choose either the horizontal vertical or the diagonal antidiagonal bases to measure these photons. Then after Alice and Bob have sent and received this information, they exchange what bases they used for sending/receiving publicly. Once they see the bases that the other one used, they will know exactly what bits of information they both share in common. Keep in mind that not all bits are retained in this information transfer. If done with a high number of bits, there will be enough information to securely transfer information across. Let's transition now to a brief demo which displays this. So as you can see here in this Jupyter Notebook, Alice will randomly generate a string of bits. Then for each bit, Alice will send the information using one of the bases, and Bob will receive and measure them here. Please keep in mind that this code does not actually reflect what is physically happening, it is just a representation of what happens when we use this type of method. Since Alice and Bob use different bases to measure, we can see that the results don't always line up. Clearly, this is a different bit string than this one. Of course, keep in mind that they both don't know what each other's measurements are, they just know which bases they use to measure. As soon as they see which bases the other person used, they can infer which bits they share in common. Therefore, the retained message would end up looking something like this here. Now, if we run multiple trials, we can see the message trend between Bob and Alice. This graph here shows 100 trials, each with a 10,000 bit string. As you can see, the data falls between 49 and about 52% of message retention, meaning that about half the message is retained. Now let's go back to our slides and look at what would happen if someone were trying to intercept it. Now let's say Eve is trying to intercept the message Alice is sending to Bob. The only way Eve can even try to intercept the message is by randomly selecting a basis pair and sending a random photon to Bob. As stated in the no-cloning theorem, it is simply impossible to make a perfect copy of a photon without prior knowledge of its state. Therefore, as soon as Eve intercepts a photon from Alice, it is simply impossible to send that same exact photon to Bob. By doing this, she is increasing the amount of information lost between the transfer between Alice and Bob, which will alert them that someone is intercepting their message. Looking back at the demo, I have implemented a way to sort of simulate someone intercepting the message, all done through this condition here. This being said, running through the simulation again, for 100 trials of 10,000 bit messages, only about 25% of the message is retained, enough to indicate to Bob and Alice that someone is eavesdropping on them. To prove that there is a clear distinction between this, I decided to include a trial where Eve would randomly decide to listen in and eavesdrop. Therefore, it is very clear to see that there is someone intercepting based on the infographic showed at the bottom. And just a general overview, this is a general graphic of how this all would flow.
Hey everyone, my name is Tejas, and I'll be going over the development topic of our project, which is the quantum key distribution. So the BB84 protocol is one of the more simple protocols for the quantum key distribution that utilizes the Heisenberg's uncertainty principle. So how this works is in the first phase, Alice will communicate to Bob over a quantum channel. So pretty much Alice will randomly choose a basis rectangular diagonal by which to encode each bit. She begins like choosing the bits from a random string of bits, essentially. So she'll transmit a photon for each bit from that random string of bits, right? With the corresponding polarization that she chose, either rectilinear or diagonal, and send it to Bob. So now Bob receives it. He will measure the photon's polarization by a randomly chosen basis. So essentially, if they both had chosen the same polarization, then Bob can measure Alice's bit correctly. Otherwise, it's random. So that's pretty much how the first phase works. In the second phase, Bob will notify Alice over any insecure channel what basis he used to measure each photon. Alice will then report back to Bob whether he chose the correct basis for each photon. At this point, Alice and Bob will discard the bits corresponding to the photons which Bob measured with the different bases. Provided no errors occurred or no one manipulated the photons, Bob and Alice should now have an identical string of bits. Okay, so that's essentially how it works. Before they're finished, however, Alice and Bob agreed to choose a random subset of bits to compare just to ensure consistency. If the bits agreed, they're discarded, and the remaining bits from the shared secret key. The remaining bits form the shared secret key. In the absence of any noise or error, there shouldn't be any disagreement, pretty much. And if there is, then that means there's an eavesdropper. So that's how the BB84 protocol works, and how it uses the Heisenberg's uncertainty principle is that like when Bob measures, on average, it'll be 50% incorrect. So pretty much half the bits will be incorrect. And then given that Eve will choose the measurement basis incorrectly on average 50% of the time as well, 25% of Bob's measured bits will differ from Alice. So that's how the uncertainty principle plays in. I wanted to go over this first because this is one of the basic protocols and basic applications, but now we'll be going into the PNS attack, which is actually uses equipment to function, which is pretty cool. So how this works is, um, so first of all, it's a little impractical to reliably produce this, just because the equipment is relatively expensive and, not easy to obtain. But essentially, what happens is in PNS, PNS is what's called photon number splitting attack. So I'll be abbreviating that as PNS. But in PNS, Eve splits off a single photon or a small number of photons from each bit transmission for measurement and allows the rest to pass on to Bob. This would allow Eve to measure her photons without disturbing the photons Bob measures. So they developed a trick to send extra decoy pulses for Alice and Bob to measure, allowing them to detect a PNS attack. In addition, the Sarge-04 protocol is resistant to the PNS because Alice does not directly reveal her bases. Instead, she reveals a pair of non-orthogonal states in which the bit might be encoded. If Bob chooses the correct bases, he will discover that he measured one of the two states that Alice revealed. If not, Alice and Bob will drop that bit. This means that Eve does not know which bases to use when measuring her copy of the photon, even after Alice and Bob agreed on the bases used. This forces Eve to guess, which means that she will not know the bit with certainty. So that's how the PNS attack works, essentially. As you can see in the top right, there's a little actual application of how it looked like. So that's pretty cool. And now I'll be going into the uh, last protocol, which is Eckert's protocol. Um, so for Eckert's protocol, there's a single source that emits pairs of entangled pairs. So essentially, the particles are separated, and Alice and Bob each receive one particle. So Alice and Bob would each choose a random basis on which to measure their received particles. So it's kind of similar to BB-84. They would discuss in the clear which bases they used for their measurements, and for each basis that they use the same bases, they should expect opposite results due to the principle of quantum entanglement. This means that if Alice and Bob both interpret the measurements as bits as before, they would each have a bit string, which is the binary complement of the other. Either party could invert their key, and this would thus share a secret key. The presence of an eavesdropper can be detected by examining the photons for which Alice and Bob choose different bases for measurements. Alice and Bob can measure these photons in a single basis and a third basis, and discuss their results. With this information, they can test Bell's inequality, which should not hold for entangled particles. If the inequality does not hold, it would indicate that photons were not truly entangled, and thus there may be an eavesdropper present. Um, as a quick picture, I'll pull up right here. This is also an example of how it looked like. So kind of similar to the protocol mentioned earlier, the PNS attack, except that essentially the channel is like distributed to each of them, and then Eve is in the center versus kind of a channel going from Alice to Bob, and then Eve could be in the middle. But yeah, those are developments of this topic.
Here, we will talk about the state-of-the-art technologies for quantum key distribution systems. There are three technological components for creating a physical quantum key distribution system that we will explain today: bit generation, bit transmission, and bit measurement and detection. To generate a quantum bit, we must first generate a photon. We can send a laser beam through a powerful attenuator, a device that reduces the power of a signal to weaken the laser until it emits a single photon. To have this photon represent a quantum state, we can polarize the photon in a specific direction with a polarization filter. Another way of creating a single quantum state for quantum key distribution is by using nitrogen vacancy. Nitrogen vacancy occurs when a nitrogen atom replaces a single carbon atom in a diamond lattice, leaving a vacant area where single qubits may be generated. However, this method is yet to be fully explored and utilized. To transmit qubits, we must ensure the qubits are sent through a controlled environment to prevent noise from disturbing or altering qubits. Fiber optic cables can be used to transmit photons between Alice and Bob over relatively small distances of 307 kilometers. However, in real-world application, fiber optic cables are bound to carry many quantum bits from other signals aside from Alice and Bob, which may cause some photons to be lost in transmission due to the noise generated from other photons. To avoid noise from these other signals, photons between Alice and Bob can also be generated through free space. However, atmospheric turbulence and the refractive index of air may also create noise and cause some qubits to be lost in transmission. To transmit qubits over larger distances, we can bounce photons off of satellites to allow worldwide quantum bit transmission. However, not enough satellites have been made to enable this. China in 2016 launched the Quest satellite, which has reportedly successfully allowed for quantum bit transmission via satellite. In order for Bob to measure and receive the qubits transmitted by Alice, he must first generate a random key to create a measurement basis for the qubits. The goal for creating a key is to make sure that it is truly random to prevent Eve from guessing the key. One way of creating this key is by sending photons through a beam splitter and measuring the state of the photons to determine on which basis will Bob measure the incoming transmitted photons. It is impossible to predict Bob's key if generated this way. In order to receive and detect individual qubits, the best technology we currently have are superconducting nanowire single photon detectors. However, they can only operate at temperatures under 3 degrees Kelvin and are extremely expensive to produce and maintain. Single photon avalanche detectors are used in place of these and in common practice as they are typically cheaper and do not require these extreme conditions to operate. However, they are slower than their counterpart.
I will now discuss open problems regarding QKD's performance, cost, and practicality. It is important that QKD possesses these qualities to allow for its use in real-world applications. Efficiency and low cost are two of the most important factors. These can be obtained with the right hardware. This hardware needs to reduce the overall cost, increase efficiency, while solving the problem that distance plays in the process. Currently, QKD is useful because it allows for higher secure rates for a more frequent update of encryption keys. This is practical because the keys generated by QKD can be used in many different types of cipher schemes, such as symmetric. A major issue that needs to be addressed is the rate of communication. Classical and QKD can currently accomplish. Currently, Classical can achieve speeds of 100 gigabits per second per wavelength channel. On the other hand, QKD has speeds as fast as megabits per second, but this is only practical for video transmission, whereas the Classical method can handle many different types of data. In order to allow for QKD to transmit higher rates of data, new hardware needs to be developed to increase the rate of generation of secure keys. Distance is another factor that has raised many new questions regarding QKD's practicality. Currently, QKD uses single photon detection, resulting in low noise or interference. These detectors determine the success and range of the system, creating some problems. Larger distance between detectors results in channel loss and eventually reduces the key rate. The lower the key rate, the less practicality QKD holds for real-world applications. This issue needs to be addressed in the future for QKD systems to be more practical, cost-efficient, and secure.